So we had already begun to talk about logistic regression in class before we got moved to a distance learning format because of the coronavirus. But so that all of these videos can be self-contained and to explain it again, because it's been a little while since we last met, I'm going to try to present it all here in just kind of a self-contained way. So I want to start with just a review of where data comes from. So we know that when we encounter data, we have these little vectors of data. So these are vectors of features. And the way I have been explaining this in class, these are kind of like frogs that we might come across. Like frogs have different properties. Some of them are green and some of them are purple. Some of them are big and some of them are small. And we've mostly been doing, well, we've exclusively been doing supervised learning, and in that you get an associated label with each one of these frogs. So when you're doing classification, you might be classifying each of these frogs into species like bullfrog, peeper frog, red poison tree frog, and things like that. And in regression, these are real numbers, so predictions about numerical properties of the frog, like hop length or something like that. You try to predict that from the features of the frog. So where do those come from? We kind of think of those as coming from some probability distribution on the input space. So for each instance, there's a certain probability that it will occur, and for each of these labels, you have a certain probability that that label will be associated with that instance. Um, so this sort of generates frogs the same way that the probability distribution on flipping a coin generates heads and tails. You can draw from that probability distribution. There's a 50-50 chance. There's a probability distribution on a six-sided die. You can draw from that by rolling the die. So by drawing from this repeatedly, we generate the instances. And then one way to kind of conceptualize what happens after the instances are drawn is the label is slapped on there by this conditional probability distribution. So this makes a frog, and then this assigns the species to a frog. It's probabilistic assignment based on its features. Okay, so the idea with logistic regression is we are going to learn this function in the case when y is in the set -1 or +1. So this is just binary classification. So if it's binary classification, why is it called regression? So this is a little bit confusing. It's regression because we're trying to learn to predict the values of a continuously valued function, which is that function. So that outputs probabilities. So it is a continuous valued function. It's a real valued function. So you can do sort of a regression on it like you would any other continuous function. So that's the idea, basically. Okay, so the idea here is that we again have some vector of weights. You can think of just as this sort of the internal state of the learning machine, or whatever. And so a certain x bar will come along, a certain frog will be encountered here, and we want to assign a probability to, well, we want to produce a number that reflects the probability that y is equal to +1 given this particular x. And so this w, for now we'll just think of it as a black box, but x together with this w will result in some probability prediction p hat. So p hat is supposed to approximately be the probability that y is equal to +1 given x. Okay. So one way to understand where logistic regression comes from is to think of the natural error that you might assign to this probability here. The idea is, well, w will generate this, and there will be some associated error. So based on this error, we can then sort of improve W, and then W will encounter more X's and make more probability predictions. We'll assess the error of those predictions and then improve W. We keep doing this over and over and over again until W is really good. So what we need really is an error function for p hat. So what should we call the error of p hat? So we're going to give a pointwise error metric. That means that it depends on a particular input x bar. So we'll say that the error of W on the input xy is equal to minus natural log of p hat. So p hat, again, is the probability prediction, if y is equal to plus 1. And it's going to be equal to minus natural log of 1 minus p hat if y is equal to minus 1. Okay, all right. So why is this a good error function? Well, one reason it's good, which is not at all clear right now, is that it just works well in terms of calculus and doing the derivatives and finding the optima and things like that. But another reason it works well is because it punishes the bad and rewards the good. So we can get an idea of why that's true by looking at some plots. So let's go over here to this Jupyter notebook. So what I have done here is I've just plotted both branches of that piecewise defined function that I just showed you, the error function. So if y is equal to plus 1, then we get this curve, which in my display here looks kind of golden. And if y is equal to minus 1, then we get this blue curve. So suppose that y is equal to plus 1, and down here we have p hat. So if y is equal to plus 1 and p hat is saying that the probability that it's plus 1 is 0, then we should spank p hat pretty hard, because that's a terrible disagreement. On the other hand, if y really is plus 1 and p hat is saying that the probability that y hat is plus 1 is close to 1, then the error is 0. So we should assign 0 error for that. And you can see that this error function does exactly that. So conversely, if the true label is minus 1, then what should the probability, what should be the penalty for p hat being close to 0? It should be very low, because that means that we're predicting that the probability that the label is plus 1 is 0, which is exactly right. And that is reflected here in the fact that the blue curve is way over there. And so there's 0 error there. On the other hand, if y is minus 1 and the thing is predicting with 100% certainty that y is plus 1, then it should be punished severely. And it is over here. Okay, so this is a good error function, just in the sense that it emphasizes what it should emphasize, and it also turns out to be good in other ways too. So now we have another problem, which is we have this kind of black box situation with exactly how you get from W, sort of the state of the learning machine, to p hat, the prediction. So we need some way of doing that, and we want this to be a continuous function of W and X and Y, because we hope to use calculus to minimize the error now that we have an expression for it. So a natural idea is to take some kind of function that goes continuously from 0 to 1, because that's the range that p hat should be in anyway. P hat is supposed to be interpreted as a probability, so it's natural to try to build things around a function that goes from 0 to 1. So this is an example of a sigmoidal function. Sigmoidal is just a fancy way of saying S-shaped. And in particular, it's the Logit function. And one way to describe it is 1 over 1 plus e to the minus s. So s has nothing to do with w, x, or y. So we still have a little bit more work to do. This is just going to be one piece. So really any other function that looks kind of s-like might be a candidate for playing this role. And there are some other functions that are s-like arctangent and hyperbolic tangent, and they both, all of them have pretty good analytical properties, meaning they have simple derivatives and they're continuous and behave well and things like that. And so arctangent is not in the right range. It goes from minus pi over 2 to positive pi over 2, but you could scale it and fix that problem. And hyperbolic tangent goes from minus 1 to 1. And actually, if you are interested in doing a little bit of algebra, just as an exercise, you can see that if you shift and rescale hyperbolic tangent so that its asymptotes are correct, 0 and 1, then you end up with the same expression as the Logit function. So now that we have the Logit function, what are we going to do with it? So when we've been doing this linear model stuff, what is it that makes a linear model a linear model? A linear model is a linear model, basically because it involves the dot product of the weight vector and the instance vector x. So let me come back here and write down that expression. Oops, I'm on the wrong screen. So we have here w bar dot product x. Okay, so we've been dealing with this a lot. So this is sort of, the starting point for linear models. When we did linear regression, what we did is we just found the weight vector w that sort of was the best just for this expression itself. This produces a value that's in the range minus infinity to infinity, so that works well with regression, because you can sort of use this and interpret the output as y, which in a regression scenario is just the real number associated with the instance x. When we did classification, we thresholded it by, man, I'm so trained to do numpy, I'm writing np.sign instead of sign. When we did classification, we built our hypothesis space around sign wrapped around this thing. So this, of course, produces a value that's just in the set minus 1 and 1. And then we kind of interpreted this as y, the true category that x bar belongs to. So now what we're going to do is we're going to wrap the Logit function around wtx. So now this is a value in the range 0, 1. And we're not going to interpret this as y, we're going to interpret this as the probability that y is equal to plus 1 given x. Okay. All right, so this has been a nice length video. I'm going to stop it here and then pick up again in a new video.